Scan a busy, modern airport terminal today, and you will quickly find automated physical machines integrated into almost every single surface. We often view point-of-sale terminals, our digital televisions, and traffic lights as standalone tools, static objects waiting for a human to provide the next instruction. In reality, these devices are active, interconnected nodes. They are the physical manifestations of intelligent systems. By definition, an intelligent system requires three specific capabilities: an embedded, internet-connected computer, the capacity to gather and analyze data, and the ability to communicate with other systems. This architecture aims to remove the human from the loop, allowing a vastly larger automated network to manage itself. To understand the data infrastructure of the modern world, we must rigorously architect the anatomy of an intelligent system from the ground up. This framework replaces the concept of isolated software with a new model, the distributed, hardware-embedded ecosystem. We begin with the machine base, the raw physical hardware of a device before any intelligence is introduced. Without localized processing, this hardware is inert. It cannot scale or respond to environmental changes without external manual control. This necessitates the first pillar, the embedded, internet-connected computer. This compute must be embedded directly into the hardware. Localized processing ensures the machine can function immediately without relying on the latency of remote cloud servers for basic tasks. An internet-ready computer inside the chassis prepares the machine for a continuous stream of external interactions. This addition transforms a static tool into a dynamic platform, capable of hosting the logic required for true intelligence. Once the compute layer is set, the system must interface with its physical environment. It needs the ability to see and measure. This is achieved by gathering raw data from its surroundings. This data takes many forms, from a smart meter's temperature readings to a traffic light's motion detection. Gathering is only the first step. The system must also possess localized analysis to interpret those signals. Unlike a passive sensor that merely records a value, an intelligent system processes that information to arrive at a conclusion. This internal loop of gathering and analyzing is what enables independent machine action. While our node is now locally capable, it still requires the third pillar, external communication. This machine-to-machine communication allows separate systems to share their analyzed data across a network. The defining characteristic of this communication is autonomy. To function at scale, data must transfer across the network without requiring human-to-human or human-to-computer interaction. In modern infrastructure, the human interface is often a bottleneck that prevents systems from reacting at the speed of the data they generate. This human-less architecture provides the fundamental building block for the developing Internet of Things. By completely removing the human interface, it allows the entire digital infrastructure to operate and scale at lightning-fast machine speeds. When we apply this single architectural blueprint across the globe, we see its universality. This design supports factory automation, advanced field and service robotics, and assistive robotics in industry. The same triad of compute, analysis, and communication is found in modern military hardware, critical medical care devices, and visual surveillance networks. We see it in the high-stakes world of character recognition and biometric identification. Systems that identify humans through faces, fingerprints, or irises deal with incredibly complex data, yet they rely on the exact same underlying node architecture to function. Whether the physical chassis is a factory arm or a biometric scanner, the engineering blueprint of the intelligent node remains the same. The mass connection of these nodes creates a globally connected network, an environment where data flows through an entirely automated landscape. Our journey from an inert machine to a fully autonomous system illustrates the transition from simple tools to complex nodes that compute, analyze, and communicate. This triad, embedded processing, autonomous analysis, and human-independent communication, is the definitive blueprint for modern AI. This architecture moves computer science away from building isolated programs and toward engineering continuous, interactive physical environments. As the Internet of Things matures, almost every imaginable physical object will be assigned a unique identifier and integrated into this autonomous grid. Modern systems engineering finds true intelligence by designing structural autonomy that operates far beyond the limits of human oversight.